On March 6, 2025, at 5:30 p.m. Central Time, SpaceX launched its 8th test flight of the Starship mega rocket from Starbase in South Texas. The launch, initially delayed due to technical and weather issues, saw the 400-foot-tall rocket, comprising Booster 15 and Ship 34, lift off smoothly. About 2.5 minutes into the flight, Booster 15 separated and was successfully caught by the chopstick's arms, marking the third such retrieval and the second time both launch and catch occurred in one mission. This achievement is crucial for reducing launch turnaround time and costs, advancing SpaceX's goal of a fully reusable system. However, Ship 34 faced a significant anomaly during its flight over the Gulf of Mexico, with reports and a video on X suggesting a possible engine explosion. This issue echoes problems from Flight 7, where Ship 33 was lost due to a propulsion leak. While not yet confirmed by SpaceX, potential causes include harmonic oscillations, ruptured propellant lines, engine failures during re-entry, or issues with the thermal protection system, which was stress-tested by removing some heat shield tiles. An unexpected aspect is that SpaceX intentionally designed the re-entry profile to push Ship 34's structural limits, including stressing the rear flaps at maximum dynamic pressure, which may have contributed to the anomaly, highlighting the experimental nature of these tests. On March 6, 2025, at 8:12 p.m. Pacific Standard Time, SpaceX conducted its 8th test flight of the Starship mega rocket system, a pivotal moment in the development of the world's largest and most powerful launch vehicle. This flight, launched from Starbase in South Texas at 5:30 p.m. Central Time, aimed to achieve several key objectives, including payload deployment, re-entry experiments, and testing the thermal protection system. However, while the mission marked significant progress with the successful recovery of the Super Heavy Booster 15, it was marred by an anomaly with the upper stage, Ship 34, potentially involving an engine explosion. This report provides a comprehensive analysis of the events, drawing from the provided transcript and additional context to ensure a thorough understanding for both enthusiasts and professionals in the space industry. The Starship program, led by SpaceX, is designed to create a fully reusable spacecraft system capable of carrying crew and cargo to Earth orbit, the Moon, Mars, and beyond. It consists of the Super Heavy Booster and the Starship upper stage, both powered by advanced Raptor engines using liquid oxygen and methane. Flight 8, involving Booster 15 and Ship 34, was the 8th test flight, following a series of iterative tests to refine the system's design and operation. The launch, initially planned for earlier in the week, faced multiple delays due to technical issues with both stages and weather concerns, underscoring SpaceX's commitment to safety. On March 6, 2025, at 5:30 p.m. Central Time, the 400-foot-tall rocket lifted off smoothly, clearing the launch tower and beginning its ascent. This smooth liftoff, powered by 33 Raptor engines on Booster 15, was a testament to the engineering behind the system, with the vehicle performing as expected in the initial phase. Approximately 2.5 minutes into the flight, Booster 15 separated from Ship 34, initiating its descent back to Earth. The booster executed a series of precise maneuvers, including a boost back burn to reverse its trajectory and a landing burn to slow its descent. This culminated in a successful catch by the launch tower's mechanical arms, known as chopsticks, a novel system designed to revolutionize rocket recovery. This marked the third successful retrieval of a Super Heavy booster and the second instance where SpaceX achieved both a Starship launch and a booster catch in the same mission. The significance of this achievement cannot be overstated. By catching the booster directly at the launch site, SpaceX aims to reduce turnaround time between launches and minimize refurbishment costs. This method, distinct from traditional landings on drone ships or land-based pads, could potentially enable multiple launches per day, a critical step toward rapid reusability and sustainable space exploration. The chopstick system, as detailed in various reports, involves colossal mechanical arms attached to the launch tower, measuring 18 feet tall, which catch the descending booster with precision. This system's success in Flight 8, as observed in real time, had SpaceX staff erupting in cheers, a moment described as a day for the engineering history books in an X post. Elon Musk. While the booster recovery was a triumph, Ship 34 encountered a significant anomaly during its suborbital trajectory across the Gulf of Mexico. Reports, including a video circulating on X, suggested a possible engine explosion within the spacecraft's engine compartment, an issue reminiscent of Flight 7, where Ship 33 was lost due to a propulsion system leak. This anomaly, observed during the high-stress reentry phase, has not been officially confirmed by SpaceX as of a launch date, leaving room for speculation and analysis. Harmonic oscillations. Persistent vibrations in the propulsion system may have led to leaks above the engine bay shielding and below the aft dome, an area referred to as the attic. Ruptured propellant lines. The powerful vibrations could have caused propellant lines to rupture, resulting in uncontrolled leaks and potential engine explosions. Engine failure. A critical failure in one or more of Ship 34's Raptor engines during reentry, given the high thermal and mechanical stresses. Thermal protection system issues. SpaceX intentionally removed some heat shield tiles to stress test vulnerable areas, which may have led to unexpected thermal issues during reentry, compromising the vehicle's integrity. Extreme testing profile. The reentry was designed to intentionally stress the structural limits, particularly the rear flaps, at the point of maximum dynamic pressure, potentially exceeding the vehicle's capabilities. These factors, combined with the experimental nature of the flight, suggest a complex interplay of design challenges and operational risks. The Raptor engines, known for their full-flow stage combustion cycle and ability to operate efficiently in both sea level and vacuum conditions, are among the most advanced rocket engines ever developed, yet their versatility introduces additional complexity and potential failure points. Improvements and objectives. Building on previous lessons. Prior to Flight 8, SpaceX implemented several improvements to address issues encountered in previous flights, particularly Flight 7. Ship 34 featured redesigned forward flaps to reduce reentry heat exposure and simplify mechanisms, enhancing durability. Increased propellant volume. A 25% boost to enable longer flights, supporting extended mission profiles. Additional vents, added to the aft section to mitigate issues like those seen in Flight 7, improving pressure management. Extended static fire test, lasting nearly a minute. This test cycled the 6 Raptor engines through multiple thrust levels to recreate flight conditions, providing valuable data for hardware upgrades. These enhancements were part of SpaceX's iterative approach, aiming to increase reliability and performance. The objectives of Flight 8 included deploying 4 Starlink satellite simulators, conducting multiple reentry experiments to gather data for future recovery missions, performing a single Raptor engine relight in space to test orbital maneuver capabilities, and assessing the thermal protection system under stress by removing some heat shield tiles. While the anomaly with Ship 34 may have impacted the completion of these objectives, the data collected will be crucial for refining the Starship system. The launch of Flight 8 came after SpaceX completed a comprehensive safety review and received approval from the Federal Aviation Administration, FAA. The FAA issued a license modification for Flight 8 and beyond, allowing operational changes, such as procedures for the flight termination system. Notably, the mishap investigation for Flight 7 was still ongoing at the time of launch, highlighting the complex regulatory environment in which SpaceX operates and its ability to address safety concerns while continuing its ambitious test program. The mixed results of Flight 8, with the successful booster catch contrasted against the Ship 34 anomaly, underscore the challenges of developing a revolutionary space transportation system. SpaceX's approach, characterized by rapid iteration and acceptance of risk, has driven significant progress, but it also means learning from failures. Key areas for future improvement include addressing harmonic oscillations, refining the heat shield design, investigating the possible engine explosion, and ensuring structural integrity under extreme testing conditions. This flight's outcomes can be compared to previous milestones in space exploration, such as the early space shuttle program, where each flight was a learning experience and successes were built upon previous lessons. The successful booster catch is akin to SpaceX's first Falcon 9 booster landing on a drone ship, a moment that revolutionized the industry by proving rocket stages could be reused. Flight 8's achievements and setbacks reflect this iterative process, with the booster recovery echoing the innovation seen in Flight 5, where the chopstick system was first prominently featured. Starship Flight 8 on March 6, 2025, was a mixed bag of triumphs and tribulations, with the successful recovery of Booster 15 marking a critical step toward rapid reusability, while the anomaly with Ship 34 highlighted ongoing challenges in developing a fully reusable upper stage. The data gathered will be invaluable for future improvements, addressing issues like harmonic oscillations, thermal protection, and engine reliability. As SpaceX continues to push the boundaries of space exploration, each flight brings us closer to the vision of routine missions to the Moon, Mars, and beyond, with lessons from Flight 8 shaping the path forward.